So welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. So please try to recall what we were studying in the last class. We saw essentially that because of using a very simple chart sharing model, you can calculate or you can derive what is the chart sharing ratio. So the chart sharing ratio was CSN divided by CBL plus CSN. Therefore, we saw that CSN has to be a certain percentage, at least 10 to 15% value of that of CBL. If CSN is much smaller than CBL, what suffers is your delta VBL, or the amount of voltage difference before and after the read operation. And if the difference between if delta VBL is very small, then it will have big problems at the sensing circuitry, because the sense amplifier will not have enough noise margin. Okay, so with this, what we will do in today's classes, we will start looking at the read and write operations which we have been doing throughout this course using timing diagrams. So this is the circuitry, or the very simplified model that we had studied in the previous class. So we are assuming that the voltage on the storage node is VDD, or you have a logic 1 stored, and we also explained in the last class why the bit line value has to be VDD by 2. That is because if it is VDD by 2, there will be an influx there will be a positive gradient between the storage node and the between the bit line when you have VSN equal to VDD, and therefore the bit line will get charged and it will get discharged when VSN is equal to 0. Okay, so with this idea, let's begin. So what we were seeing essentially was that you had your bit line charged to VDD by 2, and what we are going to do throughout in the timing diagrams in this particular course is see how the voltage across different nodes, or different the voltages on the bit line, on the storage node, on the word line, how will they evolve as you close the switch. So closing the switch essentially means turning on the access transistor. Okay, so let us see that how does the different voltage nodes evolve as a function of time. So in timing diagrams, we already know the x-axis is time and the y-axis is voltage. So what are the different voltages? The voltage, you have your 0, you have VDD, so you have 0 and you have VDD, and you have VDD by 2. Why are you tracking VDD by 2? This is because the bit line is actually at VDD by 2 in this open condition. When the word line has not been turned on, the pre-charge value of the bit line is VDD by 2. For the word line, because word line has not been asserted here yet, the value of the word line as encoded in red color or red mark is in 0, and the value of the storage node is VDD. Okay. Next, what we are going to do is we are going to turn on the word line. We are going to turn on the word line, and as a result, we can see that the access transistor will be turned on, or in very simplistic terms, the switch which disconnects the bit line with the storage node will also be turned on. Okay, and I don't want to repeat the formula that we had seen last time, where the delta VBL due to the simple charge sharing model will be VDD by 2 multiplied by CSN divided by CSN plus CBL. Okay, but however, in this timing diagrams, we see something very curious, and that we see is that the voltage on the word line, okay, remember the word line is connected to the gate of the access transistor. The voltage of the word line generally in the SRAM cell goes from 0 to VDD. Okay, it goes from 0 to VDD to turn on the access transistor. But however, in this case, as you can see from this marking, the red marking, that the voltage that you are applying on the word line is actually slightly more than VDD. And this voltage, which is slightly more than VDD, is called the bootstrap voltage. Okay. So this word line is asserted to V bootstrap, which is slightly more than VDD. And this process is called bootstrapping. So think a little bit carefully. Why are you doing this bootstrapping? I will come back to the answer very soon within this slide itself. Why are you asserting the word line of the transistor to more than VDD? Let me give you a hint. The hint is there in the meaning of the word bootstrapping itself. So what is the meaning of the English word bootstrapping? Well, very loosely, you can translate it to the Hindi version called jugaad. So what is jugaad or what is bootstrapping? It is that you don't exactly know how to solve a particular problem. You are constrained by certain resources, but how can you effectively, with whatever you have in your hands, whatever resources you have in your hands, can you somehow manage the situation? That is the concept of jugaad or bootstrapping. So think, what are you trying to manage over here? Think a little bit more carefully. Okay, let me leave you with that question for a few minutes and then proceed to what happens when the transistor is turned on. When the access transistor is turned on, naturally, please try to think what will happen to the bit line voltage and the storage node voltage. Naturally, because there is a positive gradient from the storage node to the bit line, a read current will flow from the storage node to the bit line. And as a result, due to charge sharing, the voltage on the storage node, as indicated by the green highlighter mark, will start coming down, and the voltage on the bit line will start rising up, right? Voltage at the bit line was VDD by 2, at storage node was VDD. Once this transistor is turned on, you will see that the voltage on the storage node will start dropping, and that of the that on the bit line will start increasing. And at one particular time, it will so happen that there will be a sufficient, both of them will become equal or almost equal, and there will be sufficient voltage difference between the original bit line. Remember what this delta V is? This delta V is your delta VBL. Delta VBL was the difference between your pre-charged VDD by 2 voltage on bit line and the current voltage on the bit line. So when this delta V becomes sufficiently large, remember this delta V, BL is a function of your VDD by 2 and also your CSN and CBL. So when this becomes sufficiently large, the external circuitry, which consists of the sense amplifier. So the sense amplifier is in the external circuitry. It says, I have been able to read whether there is a positive or negative change in the bit line. There is a charging or discharging in the bit line, and therefore the sense amplifier is enabled. That means the sense amplifier has been able to detect either a positive change or a negative change over the original bit line voltage. Okay. And this is essentially the read process. Remember, the read process is where you are able to find out the storage node consists of either VDD or 0 by checking whether the new value or the change in the bit line is either positive or negative. And the amount of time that it takes for this process to happen from the starting of the word line to getting enough sense margin is known as the read time. So delta T is the read time. Remember, x-axis was the time axis. Okay. And with this information, I want to bring you back to the question. Why did you have to go through this trouble of doing bootstrapping? So let us look at this question again. And we will do that again by using some very, very simple equations. I'll tell you what are the assumptions we are making in these equations. But even after these assumptions, you will see that it gives you a lot of important, insightful meaning. So let us assume that we want to calculate what is the change in the charge when you had the charge sharing model, what was the difference in the charge of the bit line before and after the switch was turned on. Okay, so after the read process, how much charge was added to the bit line? In this case, it will be added because there is an inflow of charge, inflow of current, okay, so, into the bit line. That will be equal to your CBL. It should not be delta, CBL. CBL is constant, so there is a typo over here. Please ignore this delta CBL. This will be CBL multiplied by delta VBL. Delta VBL is the change in the bitline voltage due to charge sharing. So basically the charge sharing, the change in charge will be CBL multiplied by delta VBL. Now you can also say, you can represent this delta QBL or the change in the charge by a very simple equation. Remember, charge is nothing but current multiplied by time, or current is rate of change of charge. So you can write delta QBL as I read multiplied by delta T read. Okay, I read multiplied by delta T read will roughly give you what is the charge transfer that happened during the read process. Now, of course, I'm making certain assumptions here that you have to that we have to discuss about, and that is that I am assuming that I read is just the average current. Of course, in transients there is nothing called constant I read. I'm just saying that this is the average read current that flows throughout the process of the read transients. Okay, so I read into delta T read is what I have replaced the LHS of the first equation, and that will be equal to CBL into delta VBL. Okay, so if I rearrange the terms, delta T or the read time or the read duration or the read latency will be nothing but CBL multiplied by delta VBL divided by I read. Now I would like to ask you the question, in case we always want read process to be faster, CBL is constant, delta VBL as we have designed will also be constant because CSN and CBL are constant, VDD is constant. So what can we do to ensure that your delta read is small, because you want very small read latency? The only thing that you can essentially play with to make sure that read times are small is your I read value. And since I read is the denominator, is in the denominator of the equation, somehow we have to bump up the read current. How do we bump up the read current? The methodology to somehow increase the read current is the process of bootstrapping. Remember, the current that can flow through any transistor is directly proportional to VGS minus VTH the whole squared. So VGS minus VTH the whole squared, which is also called overdrive voltage. You know, VGS minus VTH in transistor technical parlance is called the overdrive voltage. If the overdrive voltage is large, so if the overdrive voltage is large, then the read current will also be large, and as a result, the read latency will start coming down. So the entire idea of using bootstrapping is to reduce read latency. Another way of looking at it would be to say that this read current will have to flow through this resistor and capacitor network. So the best way to have a very fast discharge is to lower the time constants or the RC value of this resistor and capacitors involved in this particular circuit. And the way to do that, because you cannot really play with the capacitors, the other way to do that is to reduce the resistance of the access transistor, or in other words, increase the strength of the access transistors. Now, you don't have much leverage to play with the sizing of the access transistor. So the jugaad that you do, or the bootstrapping you do, is during the read period, what you do is you apply a bootstrap voltage. So this bootstrap voltage is a very smart way to improve read latency by ensuring that the read current is higher. Okay. However, despite doing a successful read, you have to recall that this read is essentially destructive. Why is it destructive? As you can see in the timing diagrams, that the storage node value is getting essentially disturbed, right? The storage node value initially was VDD, and now it has become VDD minus some delta V dash. Okay, so this read disturb is very evident, and therefore read is destructive. And as a result, what we have been discussing for quite some time, the data has to be written back. The data has to be written back, and how is it done is what we will discuss next. What essentially happens is the VBL is asserted to the previous value of storage node. Now you already know by the read operation, the sense amplifier already knows by the read operation what was the original value present in the storage node. We will see the exact schematic with a specialized latch design of the sense amplifier, but I'm just giving you the overall concept right now. So what essentially happens is you have an idea now from the sense amplifier what was the original value of the storage node. Now that same original value of the storage node is again asserted back on the bit line. It is again asserted back on the bit line. So see what happens is after the read is over, the value of the storage node is again charged back. So the bit line is again charged back. Remember, the bit line was in blue color. So the value of the bit line is again charged back. And since now if you charge the bit line and the word line is already asserted, the voltage in the storage node will also start charging up. And this is how you facilitate the write operation. So you did a read in the first stage, which was destructive, and to take care of that, you did a write operation, or what you called a write back operation. And this is the entire process of read and restore. So the values, as you can see, are restored. The storage node voltages we were tracking with green marker, and as you can see, after the write, they were actually restored. And as we have discussed in the previous class, since anyways there is some leakage through capacitors, even if you don't do a read operation, even when your memory is idle, you have to keep doing this cycle of read and write, or read and write and restore every 64 milliseconds. So this periodic cycle of read and restore has to be done every 64 milliseconds, even if you do not do a specific read operation. And that is because there is leakage that happens through the storage node of the capacitor, something that we discussed in detail in the previous class. Okay, just for completeness of discussion, we looked at what happens when the storage node value is VDD is 1. Let us look through another set of graphs which I have plotted in the bottom half over here to what happens when the value of the storage node was 0. So if the value of the storage node was 0, see the value of the storage node is now indicated by orange line, and the value of the bit line is going to be indicated by this blue line. As you can see that once the word line was asserted, now because storage node has 0 and bit line has VDD by 2, the read current will flow from the bit line into the storage node. Therefore, the value, the voltage on the storage node will increase and that of the bit line will reduce, and that is exactly what is shown in this graph. So the value of the bit line is reducing and that of the storage node is increasing, and at a sufficient time, a negative VBL minus delta VBL, initially VBL was positive, now VBL is negative, gets developed, and therefore the read cycle is completed. And in the write restore, what is essentially done is, since we know because negative VBL was developed and sensed by the sense amplifier, it will again assert back the value, original value of storage node, whatever was the value of storage node, back on the bit line. So the bit line is again charged back to 0, and as a result, because the word line is asserted, so they are essentially not isolated, they are connected to each other, slowly the storage node value will also go back to the value of 0. Okay, so the initial value of the storage node was also 0, and through this read and then write back, you were able to put the value of or restore the value of the storage node back to 0. So this is a complete timing diagram of your DRAM operation, which explains. It's a little complicated. I have tried to, and it looks a bit messy, but sometimes completeness requires that you make things slightly more messy. So the top half is which is indicative of what happens to the storage node and the bit line voltages when the internal storage node is 1, and the bottom half is indicative of what happens when the storage node is 0. Okay, so with this, we will go to the last part of our discussion today. What we will try to understand is this read and write back. How is it facilitated? Now, it's common sense that the read and write back has to be facilitated by the peripheral circuitry, and the write back is actually assisted by this very specialized sense amplifiers. Now, what are these sense amplifiers? They are your latch based sense amplifiers, which are specifically designed in DRAM peripheral circuitry for sensing what is the voltage on the bit line. Okay, and how is it done? During the read cycle, what essentially happens is, you see, I have expanded the sense amplifier and try to show you what is happening inside the sense amplifier or the circuit inside the sense amplifier, which is enabling this write back mechanism. So what essentially happens is, during the read cycle, you have two, as you know, the sense amplifier needs to have two inputs. One is the reference or the bit line true and the bit line complementary. Okay, so you have the bit line complementary and bit line true, and the reference node is the complementary and the true comes from the DRAM cell. Okay, so first what is done is, both the reference and the true line both are charged to VDD by 2. When the charge sharing, then what you do is you enable the word line. After you enable the word line, because of the charge sharing, there is a sufficient sense margin which gets created, and the sense amplifier is thus enabled, as we have been discussing in detail henceforth and also shown in the timing diagram. Once the sense amplifier enabled signal is generated, what happens is, the sense enable signal is thus connected with VDD or ground. Now, suppose the voltage in the storage earlier was 1, okay, or in the storage node value was VDD. Then what happens is, the bit line now seeing VDD by 2 plus delta V, and the reference, the complementary as still at VDD by 2, but here this will develop VDD by 2 plus delta V. The latch starts flipping, or it turns on and takes in the value of 1. This latch, which is inbuilt in the sense amplifier, flips and goes to the value of 1. And as a result, the value of the output of the latch is forced back into again the bit line. So the value of the latch, whatever you saw, which had gone to 1, is again forced back. We see that in the timing diagrams also, is forced back to 1. And because the access transistor is still turned on, the storage node tends to restore the value 1 by charging back from the value of bit line. On the other case, if delta V is negative, then the bit line is forced to 0 or ground by the latch, and as the access transistor is still turned on, the storage node tends to restore the value to 0 by discharging through the bit line. So this is in essence our story about read, write and restore. All of them were intrinsically tied with each other, and in the next class we will see a very interesting topic. We will see how the DRAM 1T 1C cell technology is scaling. So we will see how the scaling of 1T 1C DRAM cell happens, both at the cell level and at the system level. Thank you so much.